Hello, everybody. These are our notes 5.1. We're going to be talking about functions. And starting off, we're going to consider how we identify or classify functions as even, odd, or neither. When we consider functions that are even, they're always going to have symmetry about the y-axis. In our diagram over here, you can see that this is our y-axis, and a function has been drawn on here that has symmetry about the y-axis. In other words, if we took the right side of this function and we did a little flip from here across, we would end up matching the exact same function on this side, and that would work vice versa. Our left side would be repeated by our right side, and our right side would be repeated by that. In other words, the graph will be unchanged by any of the reflection. And specifically, it would be the reflection across the y-axis. We fold it left to right, we wouldn't be able to distinguish at all between the right side or left side. In other words, what we're saying is that the y-axis acts like a mirror. When we talk about a function that is odd, this time we make note that this is going to have a 180-degree rotation about the origin. This one is an odd function. You find the origin here, and you take this part of this graph and rotate it 180 degrees about the origin. That's going to be repeated over here on this side with no difference. And likewise, this that I've just highlighted yellow, if it were to rotate 180 degrees, it would be matched by the orange. In other words, the graph is unchanged by the rotation. You cannot tell a difference between the graph when we rotate it 180 degrees or not. And in this case, the origin is going to act like a center of the rotation. And then we have functions that are neither odd nor even, and those have no symmetry about the y-axis. Nor about the origin. In other words, it doesn't fit either one of the two above conditions. Okay. Now that's considering the graphs when we look at them, or we look at the functions and the graphs of them. Let's look at them algebraically and determine what makes something odd or what makes something even. The definition of an even function is if I enter in a value a into the function and I take the opposite of a and enter it in the function, I'll get the exact same thing. You can see from our graph up here, it would be like choosing this a value, substituting in to the function, and we would get something called f of a, and then flip over to the negative side and enter in negative a, and we'll get out something called or something that is f of negative a. Both of these will give us the exact same y value, no matter what we choose for the a. A good example, or an easy example to see this, is we know that one of our even functions is y equals x squared. And we know that f of 2 will give us 4, and f of negative 2 will also give us 4. So it's clearly an even function. Algebraically, our odd functions act this way. If we enter in the function, the value of something called the opposite of a, what we're going to get out is the value of the function at a and change the sign. Okay, so let's take a look at an example up here. And you'll see in this one that if we substitute in something called the opposite of a into this function, it's going to give us this value up here that we'll call f of the opposite of a. Then we'll take that same value of a and enter it in not as a negative, but as a positive, and check the value of the function. And we'll get something that's called f of a. And then if we compared these two would have the same absolute value. Let's take a look at another example. And this example will be of an odd function. And our easiest odd function to think of is when we have x cubed. So let's enter in here, say, f of negative 2. If we substitute in negative 2, we will get negative 8. If we substitute in 2 into the function, you'll see that we get a positive 8. Therefore, f of negative 2 equals the opposite of f of 2 and confirms that y equals x cubed is an odd function. Okay. Let's go ahead and do a quick example on this one. And we're going to compare these algebraically to determine if they are odd or even. Yes, if we wanted to, we could put this in our calculator and look at the nature of it, but let's practice the algebra on this. Okay, so our first step is to look at this and go ahead and substitute in the value of the opposite of x. So f of the opposite of x will be 3 times the opposite of x to the 5th power minus 7 times the opposite of x plus 3. Evaluating each one of these and their signs, you'll see that this to the 5th power will give us a negative value. So this will be negative 5x cubed. This times this will give us a positive value. Oops, not sure why I wrote 8, but that would be a 7x. And then we'd have plus 2. You'll see from this does not equal what we started out with. In other words, what we have shown here is that f of x does not equal f of the opposite of x. The 2's the same, but the other two terms have different signs. Therefore, this is definitely not even. Let's do the same thing by comparing the opposite of x to what we just did up above here. We calculated, we just calculated this guy, f of negative x. Let's go ahead and take a look at this function. When we do the opposite of it, the opposite of f of x will be the opposite of 3x to the 5th. That does match. The opposite of our next term will be a plus 7x. That matches. And then opposite of the third term will be a negative 2, but that does not match. Therefore, we have shown that this is not only not even, but it is also not an odd function. We've shown this algebraically. Let's go ahead and practice a few more here. Okay, so our first function, I'm going to first do it algebraically since that isn't something you've practiced a lot, and then we'll talk about the graph itself. So you can see that if we take f of negative x, this will give us a negative x squared plus 8. Negative x squared will give us a positive x squared plus 8. And you'll see that this is the same as the original function. Therefore, we show, or we can now state, that this is an even function. Yeah. Now, let's think about this real quickly and think about this graphically. We know that y equals x squared is just a parabola, plus 8 is just going to be a vertical shift of this parabola. And we know that doesn't change any of the symmetry about the y-axis. So that would confirm that this is an even function. And then also we can note now that even functions have terms that are all of an even power. Of course, x squared is an even number, or excuse me, is an even power since 2 is an even number. And you'll see that the 8 could also be written as x times x to the 0 power. 2 and 0 are both even numbers. Therefore, this is an even function. Now let's go ahead and take a look at number 2. Sorry about my little cough here. We'll get through this. And there's no need to check for odd if it is even. So let's move on to this next one. You'll see algebraically, we're going to substitute in the value of the opposite of x. And when we do, you'll see that the first term, negative x cubed, will give us a negative x times 4 will give us a negative 4x cubed. Negative x times a negative 7 will give us a plus 7. And what you can notice here is if I took this function as is and change the sign of it, this would give me negative 4x cubed plus 7x. Looks like we lost an x up here. Now we have it back. And you'll see that these two are the same. That matches our definition up here of an odd function. Therefore, we know that this is odd. Now, another thing we could do is we could graph this, and you would see that this is basically a snake type graph, a little adjustment in it. And it is symmetric about the origin. Also, like we did the last time, we could look at the exponents here, the powers. And you'll see that the first term is x cubed, and the second term is x to the first power. Both of those are odd, therefore that confirms that we have an odd function. Let's take a look at our next guy. And again, looking at this algebraically, f of the opposite of x, when we take it to the 4th power, that'll give us a positive x to the 4th times 2. And then a negative x times a negative 3 gives us a positive 3x. These are not the same. Therefore, we know that this cannot be an even function. And we can also take the opposite of that function, negative 2x to the 4th plus 3x, and you'll see that these two are not the same. Since those are not the same, then we know that it is not an odd function. Therefore, this is neither even or odd. And let's take a look at our next one. We're going to substitute in the opposite of x. This will give us cubed, a negative value of negative 8x cubed. And our next one, we'll change this to a positive 7x. And then our last term will be plus 2. This is similar to the last one that we did, with both of these not being the same. So that means that this is not even. If we change the value of the function and change it to a opposite of f of x, you'll see that the first term, negative x cubed, plus 7x, and then minus 2. These are, again, pretty close. First two terms are the same, but the last term, or excuse me, first two terms are the same. The last term does not match in sign. Therefore, this is not odd. And this is neither even nor odd. And now's a good time to, again, go back and look at the exponents here. First term, odd x cubed. Second term, odd x to the first power. Last term is x to the 0 power. This one is an even exponent. Let's try our next one. Algebraically, we're asked to show that this is odd or even algebraically. We're going to substitute in the opposite of x in each one of these and compare. Opposite of x to the 4th power will still be a positive x to the 4th power. Opposite of the x squared times 8 will also give us the same value of 8x squared. Therefore, this must be an even function, since both of these are the same. Let's go ahead and look at our last one. And by now, you might get tired of doing all the ones algebraically. So let's go back to the easier method, and that's just to look at our exponents. You'll see that we have an odd exponent, even exponent, and even exponent. When we have a combination of evens and odds, that makes this neither even nor odd. And if we were asked to show it algebraically, we could easily substitute in, and it would match the pattern that we've seen up above in our previous ones. Next thing about functions that we want to look at is when a function is increasing or when a function is decreasing. A function will be considered as increasing when we're going from left to right and we get a larger value. A function will be considered decreasing as we're going left to right on the function, we get a lower y value. Always from left to right, and you can see that this is decreasing. Now, if we start over here to the left and we go to the right, and we're at the same value the whole time, then this is neither increasing or decreasing, and it's called a constant or a constant rate. This happens every time we have horizontal lines. And then just a note for us when we're answering these, and we have something that goes from increasing to decreasing, we're going to leave those with open intervals rather than closed intervals. So let's take a look at our first example here and a quick scan of this for increasing and decreasing. We'll go ahead and do our increasing, and that's when we're going from left to right up, and you can see we're going down when we get to here. We're going up as we go from left to right, constant, up from left to right, decreasing, decreasing, and constant. So let's write this in interval notation to show when we are increasing. We're going to start here at -5 and end up at -3. So from -5 to -3, we're increasing. And then from a -1 to a +1, the function is increasing. We stop increasing until we get to a +4 value. And then we're increasing until we get to 5. Let's take a look at the decreasing intervals. Decreasing is when we go down from left to right, which is over here, not there. And then during this whole section here, we're going down as we go to the right. And interval notation, you'll see that we're starting here at -infinity. We're going to stop at -5. Then we'll pick it back up at a +1 and stop at 4. Our constant values are these remaining parts of this function when the graph is horizontal. And those occur when we go from -3 to -1, and then again 5, and then it goes constant to infinity. You want to pause the video now and practice the next two, that's fine, and then check your work. I'll go ahead and talk you through it if you want to stay on and do these. So let's do our increasing first. It appears right about here, and the graph stops dipping down and starts going up, but then it stops here at the peak as it goes through this roller coaster type curve. So our increasing, we only see one interval, and that is from -1 to a +1. Then we have a decreasing interval starting up here at infinity from -infinity, and then it stops at -1. It picks up at 1 again and starts decreasing to infinity on the right-hand side. So our decreasing interval starts at -infinity, then stops at -1, starts again at 1, and then it always decreases for the remainder of the curve. And in this case, we have no values or no point where the function is constant. This would be a none. Next one, we'll just start out again with the increasing. That's this part of the first hump. And then this little jute right here where we go up. These start here at what appears to be -6 and goes to a -4. And then starts at the origin where x equals 0 and then goes to a +2. Those are our increasing intervals. For the decreasing part, it's going to be between -4 and 0, and then from -2 over here to what is a +5. I think I said -2, but I meant to say +2 there. So again, our decreasing interval starts at -4, ends up at 0, and then starts at 2 and ends up at a +5. This one happens to have two spots where we are constant, and those are from a -10 to a -6, and then right here at the end of that decreasing interval at 5, and then stops at what appears to be 9. That's increasing and decreasing intervals. Okay. Now, before we go on to the next one, I want to point out on some of these graphs what we're going to be looking at in the next, and that is the idea of a maximum or a minimum point. Local maximums will always occur when we're up at a peak. You can see we have a peak here at the top, we have a peak here at the top, and a peak here at the top. What we're going to note on the next page is that all of these maximums always occur as we change from an increasing to a decreasing graph. Increasing, increasing, increasing here, orange. Then it changes from orange to pink, where we're decreasing at the maximum. And then again over here, increasing to decreasing, we have our maximum. And likewise, a minimum is when we dip down. When we're dipping down here, you'll see that we have a minimum over here. And that occurs when the graph is going down, 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 or decreasing, and then stops decreasing and starts increasing. A minimum here, decreasing, 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 and then starts increasing on the other side. So let's take a look at this and confirm this in our notes on the next page. A local minimum is a point on the graph where the graph itself switches from increasing to decreasing. And that's what we showed on the other side. We are increasing, 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 maximum, and now we start decreasing, decreasing, decreasing. A minimum, though, will occur as the graph is going down and decreasing and then changes to increasing. It's going to be this one. In this case, we're going down, down, down. We reach the minimum point, and then we start increasing again. Increasing, maximum. As soon as we go past the maximum, now we're decreasing. Let's take a look at these in the two graphs below. In each one of these, you'll see we repeat what we did on the other side. And I want to confirm what those are. And also make sure that I'm answering whatever question that they have. So if it is in this case, we know that our maximum on this graph occurred when we went from increasing to decreasing here at a +1. That was our maximum. Okay. So when we're answering this, if it's asking us a where question, where is the maximum, then that's asking for that x value of x equals 1. If it's asking for what is the maximum, then that's asking us to answer this with the y value of 2. So typically when we want to answer these, we'll answer this in a statement saying the local max of 2 is at x equals 1. Or you could even say local max of y equals 2 is at x equals 1. And let's do the same thing for our minimum. In this case, our minimum occurs over here when we change from decreasing to increasing. And we can answer this one the same way. We could answer it as a where question or a what question, or just plain answer both of those. The where is at x equals -1. The what is y equals -2. And in this case, the local min of y equals -2 is at x equals -1. And let's take a look at our next one. In this one, we had a local max when we went from increasing to decreasing here, a local min when we went from decreasing to increasing at the origin, and then finally, as we go down and to the right, we have a maximum. So in this one, we have two local max, where we're going from increasing to decreasing in each one of these. So our local max of, in this case, it appears to be a value of 8. So we would have at 8, and our y value appears to be at a our x value appears to be at -4. So another way that they'll ask this, maybe not in words what and where, but it could be find the point of the local min or max. Remember, if it uses the word point, then we have to answer this as an ordered pair. Our local max would then be at -4, 8, and then our other one would be over here, which appears to be a value of 4 on the y-axis and 2 on the x-axis. So this would be a local max at the point 2, 4. We'll answer the minimum also as a point, and that occurred right here at the origin at 0, 0, when we changed from decreasing to increasing. So what x, or excuse me, y, where x, a point, name both of those as an ordered pair. Now let's talk about absolute max and absolute minimum. At most, a function has one absolute max and one absolute minimum, most. And that is absolute max, absolute min value out of this. Okay. A function may have no absolute max, and it might also have no absolute min. It might even have both of those. So when would we have these? Well, let's take a look at our example up above. You'll see in this one, we have a local max here, but this arrow is going up to infinity, so there is no absolute max. And as a matter of fact, the arrow is going down in this direction, so there's also no maximum or no absolute min. The next one, in this case, our absolute max is right here. That's the highest point on this curve, and that occurs at the point -4, 8. Our absolute minimum value is 0, and we're going to say that that occurs right here at this minimum at the origin of 0, 0. Let's take a look at a couple practice problems. Again, if you want to pause the video, do your work, and then check, you're fine to do that. I'll go ahead and kind of walk you through this one. You'll see on this one that we've got increasing, increasing, and then a section of decreasing. Okay, so in this case, if I were given this problem on a test, one thing which would be a legitimate question is to ask, because you can see from some of your copies, opened or closed dot, not so sure. We would want to ask that. And in this case, these should be all closed dot. There wasn't the intention that any of these would be open dots. And you'll see from this that we do have local maximums, and the local maximums, first one's here at -220, and then the second one is at 345. our local minimums are here and here. And the first one is at -3, +10. And the second one is at a +1, -7. So these are both our local max, and this one, I'll write that down as a local minimum. Two local max, two local mins. Out of these, we will determine which ones are our absolute. And you can see, obviously, this is the highest point. So this one would be our absolute max. And on the other side of this, you'll see this is the lowest that it goes, and that occurs at 1, -7. So that would make this the absolute min. Let's take a look at our next one. And we go increasing, increasing, and another increasing with a section of decreasing in between. Therefore, our local max occurs right here at -2, 4, and then another one over here at a +5, -5. The local min occurs here at -5, -145, and over here at a +3, a -8. Out of these, the highest X value is 44. That would make this one the absolute max. The lowest Y value is at Y equals -145, which would make this the absolute minimum value. Point. Let's look at our next one. In this one, we have a decreasing interval until we get here at what appears to be a -1. And then, negative, and then an increasing, followed by decreasing, and then followed by increasing one more time. In this case, we do have a local max, and that occurs about there. And that would be, since it appears that it's on the y-axis, that would be at 0, 3, given that equation. And then, if I look at this one, I do have a set of minimums here and here. And in that case, at our local min over here at a -1, not sure exactly what that value would be, but it's less than 10. And then over here, do see that we have at a +2, what appears to be a -30. And out of these, we'll get our absolutes. Since both of these arrows are going up to infinity, that means there's no absolute max, but there is an absolute min, and that absolute min is here at the 2, -30. Now, the final thing today we're going to talk about on our functions is the idea of a rate of change. And to get an understanding of that, we need to go back to a geometry term called a secant line. And a secant line is a line connecting two points on a curve or on a graph. So if I've got this beautiful little curve here, and I pick a point here, A, and a point here, B, and then connect them, this line is called a secant line. Then we can look at the slope of the secant line, and the slope of this secant line has a special name called the average rate of change over that interval from point A to point B. So let's consider this function. F of x equals 3 times x squared plus 2x. And let's calculate or determine the average rate of change of this function, or the slope of this function. In order to do that, we need to refresh ourselves with the idea of a slope, and slope is rise over run. Three most famous words from middle school: rise over run. That is when we do a change in y, that's an up or down value, and a change in x, or an y2 minus y1 divided by x2 minus x1. So let's take a look on this interval. On this interval, we'll need to go ahead and calculate some y values. When x equals negative 2/3, we'll find f of negative 2/3, and negative 2/3 squared will give us 3 times what is that, 4/9, and then plus 2 times negative 2/3. 3 divided by 3 is 1. 9 divided by 3 is 3. So this, we could do some division first, so we don't have to simplify later. And that's going to give us 4/3. And then this is minus 4/3, which actually gives us 0. And let's check when x equals 0. When x equals 0, find f of 0. Well, that's pretty easy, because this is just going to be something times 0 plus something times 0, which is 0. So to find the average rate of this function over this interval, we're going to put those values in our slope formula, and that will be f of 0 minus f of negative 2/3, all divided by 0 minus negative 2/3. So where does that get us? Well, that just becomes 0 minus 0 divided by 2/3. 0 divided by anything is still just 0. This has an average rate of change of 0. Let's try the points, or the interval from x equals 3 to x equals 5, and see what we get. So let's start off with x equals 3 and find f of 3. This will be a 3 times 3 squared plus 2 times 3, or 27 plus 6, which gives us 33. If we substitute in x equals 5 and find f of 5, this will be a 3 times 5 squared plus 2 times 3. 5 squared is 25. You have 3/4, you have 75 cents. And then, of course, 3 times 2 is 6. 75 plus, oops, that's not a 3. That was a 5. That should give us 10. We did 3 the last time. 2 times 5 is 10. 75 plus 10 gives us 85. So now when we calculate our slope, the f of 5 is 85. The f of 3 is 33. And of course, this will be a 5 minus 3, which does give us 52 divided by 2, which is 26. The average rate of change over this interval is 26 units. There are a couple more for you to practice on, like we've done on the last ones. If you want to, you can pause the video, calculate those, and then check your answers. We're going to go ahead and find f of negative 2 and f of 5. Negative 2 will be 4 minus 4, which is 0. 5 will be 25 minus 4, which is 21. find the average rate of change, that slope. We will use those two values we just got, 21 minus 0 divided by 5 minus 2. And since that is a -2, I better change my sign there. That's going to give us a 21 divided by 7, or 3. The average rate of change would be up 3 to the right 1 over that interval. Next one, we'll substitute in f of 2 and f of 5. F of 2 will give us -3 times 8, 2 cubed, minus 2 times 2. That should give us a -34. A -3 times 125 minus 5 times 5 will be the values that we're going to evaluate when we substitute in x equals 5. The result will be -400. Our average rate of change this time will be those two values, -400 plus 34, all divided by 5 minus 2. And this should be a -366 divided by 3, or an average rate of change of -122. One more to check. This will be an h of -1 and h of 1. -1 minus 4 gives us -5. -1 plus 4 gives us a +3. The average rate for these will be 3 plus 5, or minus a -5, and 1 minus a -1, or 1 plus 1. 8 divided by 2 gives us 4. Now, the last one just uses some of the algebra that we've had before, and that is write the equation of the secant line of the function on this interval. And so in other words, we've got whatever the function might look like. We pick 2 points. If we can calculate the slope of that line and we have the points, we can also write an equation of that line. And that's exactly what we're going to do here. So first of all, we're going to evaluate the function at -2 and at 3. -2, when we substitute this in, it will give us 8. And a +3 will give us a value of 33. From here, we'll use that to find our average rate of change, or slope of the secant line, which will be the 33 minus 8 divided by the 3 minus a -2. 33 minus 8 is 25. 3 plus 2 is 5. 25 divided by gives us 5 for our slope. Since we're given some x values here and we've calculated the y values, we can easily use our y equals m times the quantity of x minus x1 plus y1, our function form, to write this equation. First of all, our slope we know is 5. Y equals a +5. X minus our x1, I'll just go ahead and use the +2 here for our x1 value, or excuse me, -2, which changes this to a +2. And then our y value, that came when we evaluated the function at -2, which is going to give us a +8. And there you have it, value of this function, or excuse me, the function that would be the equation of this line that was a secant line. We'll do one more example, see what you can do on this one. So first of all, if we want to calculate the slope of this, you'll see that we need to evaluate f of -1. F of -1 gives us -5. f of 1 gives us a positive 3. Therefore, we can calculate our slope. That's going to be the 3 minus -5 divided by 1 minus a -1, or a slope of 8 divided by 2, or 4. Now we're ready to go with our equation. Y equals the slope of 4, x minus, and I'm going to use this one this time, a -1 plus a positive 3. If it were multiple choice and that weren't on there, then they may have chosen this point. And that would be y equals 4 times x plus 1, since that's a -1, and then -5. Hope these notes have gone well for you. Please have a good day.